So hey everyone, welcome to Deliveroo. I'm Greg, and this is a talk about error handling, which might sound like an incredibly boring subject, and it kind of is, but Deliveroo's been using Ruby quite a lot for most of the last few years. Increasingly we're using Scala, and one of the questions that keeps coming up is how do I handle errors? Because it's really quite different to most languages, and it's kind of a different way of thinking. So I thought I'd do a talk about it. And I kind of need to stand a bit more to the side so people can see. So, in the beginning, God gave you Visual Basic 6. This may not be chronologically accurate, but the reason I thought we'd start with the VB6 is because I used to be a VB6 guy. This is going back many, many years. I remember when VB6 was new. And the thing is, VB6 was widely derided for basically everything, but particularly its error handling, because the way it worked, you wrote on error resume next, and then any statement, no matter what it did, wouldn't raise an error. So you had to check the error number after every statement and handle the error at that point. This was pretty tedious. The funny thing is, in a horrible mixing of metaphors from the Bible, people still like this apple. I mean, this is still how a lot of languages work, like C, still widely used. I mean, we know that's a fairly old language, but Go, I mean, an allegedly more modern language, still has really terrible error handling. We have to check the error code after every single statement to see if things have actually worked. Sorry, Go is the other popular language at Deliveroo, and I just don't get it, so I can't resist a chance to have a dig. But yeah, so people decided they wanted a bit more power than this. So on the second day, we got go-to statements. On error, go to some error handler and handle it in there. And this is great, because now you don't have to check things on every line. You can go straight to the error handler, check what type of code it is, and handle things there. Brilliant. But seriously, I mean, apart from the fact that you don't get many chances to inject VB6 into a talk nowadays, why have I started this way? Well, the thing is, exceptions are kind of the same thing, really. Like, exceptions are really just go-to statements. You do something that causes an exception, you stick an error handler in there, you go to it, handle the exception. The only real difference is that with exceptions, the go-to can be non-local, so it can return out of the function. And this can kind of make things hard to handle, because when you've got errors that can bubble up from everywhere, you don't necessarily know what you need to handle in the calling function. So checked exceptions, everyone's favorite subject. I'm really getting all the big guns in here. Checked exceptions. Checked exceptions kind of came along with the idea that it should be able to show you what a function throws. So not only what it does under normal conditions, but you know what it's going to do under exceptional conditions. So something like this, simple function to open a file and read the first integer out of it, throws IO exception, which is great, because in the calling function we now know exactly what we need to handle and exactly what this function can do. Except we don't, because the problem is checked exceptions are pretty badly designed. Like IO exception covers anything from permission denied to disks gone to pretty much anything. But it's got loads of subclasses like file not found, which actually have reasonable conditions that you might want to handle. And things like file not found, which opening the file can raise here, is hidden by IO exception because it's a subclass. Similarly, you've got things like number format exception, which can be thrown by parseInt. And that's not a checked exception, so you don't declare it, the caller doesn't need to handle it, so it's pretty much undocumented this function actually throws it. Basic idea was sound though. I mean, when you've got exceptions, you've really got two types of thing. You've got exceptions that you kind of expect, things that you really ought to handle, and then you've got exceptional exceptions, which are ones that you're not expecting to happen, things like you go and connect to your database and it's gone, or you talk to the file system, you don't have permission to read it. These are stuff that you probably can't reasonably expect it to handle most of the time. And I think I've just clicked the stop button by accident. No, there we go, just a power issue. So checked exceptions, in spite of the flawed execution, actually had a pretty good point. But these aren't the only types of exceptions you're going to come across. There's fatal exceptions. So out of memory, stack overflow, these basically mean your machine's balked, and some languages you can continue running from them. Scala, Java, that's kind of it. Any attempt to handle these things is going to make stuff worse, which is why you've got the non-fatal matcher. So you can basically make sure you don't handle any of these errors, because there's really nothing to do apart from crash. You've got hidden control flow exceptions. So things like thread death and interrupted exceptions you don't see nearly so much nowadays, because we don't tend to program with raw threads and so on. But non-local return control is a really interesting one. Right. It's kind of well known in the Scala community that you don't use return for returning from functions. But a lot of people think this is just a stylistic thing. In reality, it's actually because it can cause some major problems. Like return always returns from the method in which it's defined. So if you've got, say, a pipeline or a lambda in there, and you return from that, it's not just going to return from that function, it's going to return from the whole method that was defined in. And if you, in the worst case, you might have closed over this exception and not actually unwrap it there, and wrap it somewhere else, and you just get a bomb of this exception going off. And because it handily inherits no stack trace, you can't even tell where it came from. So, pro tip, never use return in Scala. There's always a better way. And then, finally, the last one we'll talk about today, semi-exceptional exceptions. And these are really quite common nowadays, because if anyone's used AWS, you'll be aware that most of the time you provision your throughput, and if you go over it, you're going to get a provision throughput exception. Similarly, if you're talking in the microservice world and you've hit your quota on another service, you might get 49 too many requests telling you need to back off. And a lot of the time, and the reason I said these are semi-exceptional is because hopefully it's not going to happen, hopefully using traffic shaping and token buckets to make sure you don't exceed the limits, or you're hoping your autoscaler is going to kick in and make sure it scales up your database before you get to the limits. But these aren't always going to happen. So these are kind of exceptions that you don't really expect to happen, but kind of do. And also the way you handle them is going to be kind of different as well. Like if you're in a web service and you've got, say, a 50 milliseconds latency limit, you're not going to wait for the provision throughput to come back because you can't afford to wait a second because then you'll blow your own limit. So at that point, you've kind of got to translate that into 503 service unavailable, saying that if that thing's down, you're overloaded, and then that's going to go back up the stack because the next service up's going to see that, and they'll be, again, wasn't expecting that, but that means I kind of need to back off because that service is overloaded. So 503 errors have a bad rep because a lot of services go fine, catastrophic, and everything's down. In a well-written service, you should actually be interleaving 503s when you're at peak load and you can't handle any more to protect the server. Cool, so that's the various types of exception you might come across. There's probably more, but this is only a short talk, so I didn't want to cover everything. So let's talk about modeling these things. After all, that's what this is supposed to be about. So one of the things in Scala is instead of checked exceptions where you kind of have an exception that you're supposed to handle, you've got the either type. So either is basically a type that can have one of two values, left of some kind of error type or right of some kind of value type. So for this file function, we might define a couple of error codes, file not found and number format invalid. And then we can declare our function to use the either. So this thing basically means when we read the integer, it's either going to return one of these error codes or an integer. To handle it, match on the right case, match on the left case. And the nice thing is because we've declared this trait as sealed, this is an algebraic data type, so the compiler knows that there are no other possible cases. So when it looks at this match clause, it can see that those are the only three possibilities that function can return. So if you go back, add another error code, the compiler will fail to compile, got to go back and revisit everything, which is great because it means you're always basically it documents your assumptions, and if you change your assumptions that more things can change, you have to go back and revisit all the places where you've assumed that's the case. But this function isn't quite right because it could return those things, but as we said, permissions. You might just not find you can't access the file, so it could throw. Try. So either is really for places that you're expecting to be able to handle the result. Try is kind of really where you're not. I mean, this is perhaps me being slightly opinionated about stuff, but in Scala I never use exceptions for things you're expected to handle. It's either for stuff you might handle, or try or future, which is the async equivalent, for stuff that you're just going to throw up to the top, log somewhere, and then either fail or crash. So we can rewrite the function here, stick a try around it, and this now says, great, this function is going to try and return either one of those error codes or an integer, or it might fail in some unspecified way that you're not expected to handle. And again, we can recover from that with our non-fatal extractor. Probably shouldn't, but you can. This is the kind of thing you probably only ever want to do at the top level, to just log it and then throw. But even that, this doesn't cover all the cases. What happens if the file's there? We can read from it, but it's empty. Option. So let's say we decide that's okay. Maybe that's not an error. Maybe if the file's empty, that's fine. We're going to stick some stuff in it. We can extend the signature again. So now we've got something that we're going to try to either return an error code or possibly an integer if it's in the file. Again, we can extend our handling. So this is, because option is an algebraic data type as well, the only options are sum or none. So again, we know that this is completely exhaustive and is going to handle every possible case. This can get pretty messy, particularly if you're in comprehension. So if we had more time, we could talk about monad transformers, which are a slightly divisive subject. This gives you a way to flatten these hierarchies and only be able to deal with the things you want, but we don't. So this is just kind of a summary. Your types are your assumptions. These are the different ways we can model functions. Like maybe if the only thing we care about is we want an integer or fail, it's just a try event. That's it. This function either succeeds or it doesn't. Or we can give it a much more verbose option going, these are all the things that can happen. And these aren't necessarily going to be static. Like we tend to write services and things like, we assume that in the repository layer, we might want to handle provision throughput exceeded. And so we return that as an either code. And turned out, actually, you know what, in the code base, there is no way we're handling that code. We're always just checking it up to the top level. So you go, right, well, that was the wrong assumption. Go back, modify the types, follow it through, and fix everything up. And that's kind of really the Scala way of thinking about exceptions, is your type system, well, I mean, not just exceptions in all of Scala programming, your type system represents your assumptions. Same with errors. That's it. I'm Greg Beech, and I'd be remiss if I didn't point out that we are hiring. Lots of people come and join us. It's great.